Good morning all. Today we are going to study about multi-quadrant operation in electrical drives and their steady state stability. Both these are very important topics. First we will see the multi-quadrant operation followed by the condition for steady state stability. For consideration of multi-quadrant operation, torque is represented along the x-axis and speed is indicated along the y-axis. If you see in this first quadrant, both the torque and speed are having positive sign, or we can say both the torque and speed are of positive polarity. Therefore, the power developed in the first quadrant will be also having positive sign, because as you know, the standard relation for power is torque into omega. So while analyzing this first quadrant, in this first quadrant both the torque and speed are having positive polarities. Therefore, the power developed, which is given by the equation torque into omega, will be also having a positive polarity. Positive power is indicating that the power will be flowing from the electric source to the motor. That is, the power is being supplied to the motor side. So this clearly represents the motoring operation. While looking into the second quadrant, here also in this quadrant the speed is having positive polarity but the torque is of negative polarity. Hence the power developed will be of negative sign, which indicates that the power conversion is from mechanical energy. In fact, the energy conversion is from mechanical energy to electrical energy one. That clearly indicates the generating operation, which will come into picture during braking operation in electric motors. Similarly, if you consider the third quadrant and fourth quadrants also, in third quadrant both this torque and speed will be having negative signs. Therefore, the power developed will be positive here, and in fourth quadrant the power developed will be negative. If we are assuming the speed, that is the positive speed or the speed along this direction as the forward direction, then the operation in first quadrant and second quadrant will be of forward motoring and forward braking one. Since this is assumed to be so, the operation in these two quadrants can be said to be reverse motoring and reverse braking one. The multi-quadrant operation discussed so far are expressed in a tabular column here. This will give you more understanding. If you see in this first quadrant, that is during the forward motoring, both the speed and torque are positive. So the electric power flow is also positive. So the energy conversion will be from electrical energy to mechanical one. While considering the second quadrant, it is forward regenerative braking. In that second quadrant, the torque is having negative sign. So the electric power flow will be also having negative sign, which clearly indicates that the energy conversion is from mechanical energy to electrical energy. That is, the generating operation is occurring during this regenerative braking. Similarly, the operations are explained during reverse motoring as well as reverse regenerative braking operations. For better understanding of four-quadrant operation, we will consider the case of a hoist mechanism as an example. Basically, a hoist consists of a rope wound over a drum. This is actually the rope which is wound over this drum, and this drum is basically coupled to a motor. One end of the rope is connected to a counterweight and the other end will be connected to a cage. There can be two configurations for this cage. One will be an empty cage and the other one will be a loaded cage. The counterweight is chosen in such a way that its weight will be greater than that of the empty cage but less than that of the loaded cage. Basically, this cage is used for transportation of the materials. So there can be two configurations in this cage. One is empty cage and the other one is loaded cage. And the weight of the counterweight is chosen in such a way that the counterweight will be having a weight which is greater than that of the empty cage but less than that of the loaded cage. That is indicated here. That is, the weight of counterweight is greater than that of the empty cage but less than that of the loaded cage. In this case, we have considered a hoist mechanism as an example. It's not necessary that for understanding of this multi-quadrant operation only hoist. Now we will discuss the multi-quadrant operation in a hoist. In this first quadrant, both the torque and speed are having positive signs. The positive sign of the speed is indicating the forward direction of motion. In the case of hoist operation, this forward direction of motion is assumed to be the upward direction of motion of the cage. So if you see in this diagram, as the weight of loaded cage is greater than that of the counterweight, in order to move this loaded cage in the upward direction, some external torque has to be applied in the anti-clockwise direction. That is actually provided by the motor. So the motor torque which is in the anti-clockwise direction is assumed to be the positive torque one. So this torque which is provided by the motor in the anti-clockwise direction will help to lift this loaded cage, or will help to move this loaded cage in the upward direction. There is no other way that this loaded cage will go or will move automatically in the upward direction, since the weight of this loaded cage is greater than that of the counterweight. So the only provision by which this loaded cage can be moved in the upward direction is by applying a external torque or applying the external power to this drum by using a motor. Since the supplied torque is in the anti-clockwise direction, and as the value of the torque which is delivered here is greater than that of the load torque, definitely it will bring about the upward motion of this loaded cage. That is based on the fundamental torque equation which we have discussed in our previous video session, which is represented by the relation T minus TL is equal to J into D by d omega by dt. Hope the first. Now we will move to the second quadrant operation of the hoist. In the second quadrant also, the direction of speed remains the same as that of the first quadrant, that is along the upward direction of the cage, whereas the direction of torque is opposite, because in the first quadrant the direction of torque is positive, whereas in the second quadrant the direction of torque is negative. The second quadrant operation is explained with the help of a counterweight and a empty cage. Here it was explained in detail with the help of counterweight and a loaded cage, but in this case it is explained with the help of a counterweight and an empty cage. As I mentioned before, the weight of empty cage is definitely less than that of the counterweight. So if you consider this situation, as the weight of this counterweight is much larger than that of the empty cage, this counterweight will be coming down just like a free fall condition, and this empty cage will be going in the upward direction at a very large speed. In order to limit such a high speed movement of this empty cage in the upward direction, we will be providing, or we will be producing a torque in the opposite direction of the motion of this cage, that is this empty cage. That is, the motor will be producing a torque in the clockwise direction, so that the torque which is produced by the motor will help to provide the sufficient braking required for the upward motion of this empty cage. That is, the motor will be producing a torque in the clockwise direction. Since the motor is producing the torque in the clockwise direction, this torque will help to oppose the load torque which is actually acting in the anti-clockwise direction. Hence the net effect is the motor produces a braking effect here, which helps to control the speed of upward motion of this empty cage. So comparing with the first quadrant operation, if you see here, in this case the direction of the torque which we have considered as positive one is in the anti-clockwise direction, while coming to the second quadrant operation, the direction of torque is in clockwise direction. Always the direction of load torque from the basic fundamental equation of torque equation, which is actually T minus TL is equal to J into d omega m by dt. It's very clear that the load torque will be having a direction always opposite to that of the motor torque. So in this first quadrant, the second arrow is indicating the load torque, which is actually opposite to that of the motor torque. Here the motor torque was in anti-clockwise direction, which is assumed to be the positive torque. So the load torque will be definitely in clockwise direction. But in this case, the motor torque is in clockwise direction, As in the second quadrant, the torque is of negative polarity. Always the load torque is having a nature to oppose the motor torque, so the load torque will be of opposite direction, that is in the anti-clockwise direction. In both first quadrant and second quadrant, the speed is of positive polarity, which is indicating the upward direction or upward motion of the cage. You can see very clearly that in this first quadrant as well as second quadrant, in both this quadrant the cages are moving in upward direction. In the first quadrant it is the loaded cage, whereas in the second quadrant it is the empty cage. Since in both these quadrants the direction of motion of the cages are in the upward direction, which is actually represented as the forward direction. In both these quadrants, the upward motions of these cages are indicated as the forward directions. So the first quadrant operation can be said to be the forward motoring one, and the second quadrant operation can be said to be the forward braking one. Similarly, we can discuss about the third quadrant and fourth quadrant operation. As you can see, in this third quadrant, both the torque as well as speed are having negative sign. In this third quadrant, since the speed is negative 1, it is indicating the downward motion of the cage. This can be explained with the help of a counterweight and an empty cage in the hoist system. Since the weight of this empty cage is very much less than that of the counterweight, it cannot, or this empty cage can't come down by itself. So in order to bring down this empty cage, some external torque has to be applied here in the clockwise direction. So this external torque will be provided by the motor. So it's very clear that in this third quadrant operation, the torque has to be produced in the clockwise direction. Comparing with that of the first quadrant, in the first quadrant the torque was produced in the anti-clockwise direction, but in this second as well as in the third quadrant, the torque which is produced by the motor is in clockwise direction. In this third quadrant, the torque which is produced by the motor brings about the downward motion of this empty cage. As mentioned before, the direction of load torque is always opposite to that of the motor torque. So in this quadrant, the direction of the load torque is in anti-clockwise direction. As both torque and speed are having negative polarity, the power developed will be of positive polarity, which is clearly indicating the motoring mode of operation. As the motion of the empty cage is towards the downward direction, the operation in this quadrant, in the third quadrant, indicates the reverse motoring operation. Reverse is indicating the downward motion of the cage. In this first and second quadrants, it's very clearly mentioned that the upward motion of the cage is indicating the forward direction. So if you see here, in this case the downward motion of the cage will be exactly opposite to that of the first and second quadrant operation. So the downward motion of this cage can be assumed to be the reverse direction one. In the third quadrant, in specific, it will be reverse motoring operation, as the power developed is having positive sign. Now let's see the fourth quadrant. In the fourth quadrant, the speed remains the same as that of the third quadrant, but the torque is having positive polarity. So this can be explained suitably with the help of a loaded cage and a counterweight. As shown here, the weight of the loaded cage is very much greater than that of the counterweight. So if left free, this loaded cage will be having almost like a free fall operation, and this counterweight will be moving in the upward direction, and this loaded cage will be moving in the downward direction at a dangerously high speed. In order to limit this, the motor will be producing the torque in the anti-clockwise direction. So the torque which is produced by the motor is producing braking effect here. That is, the torque which is produced by the motor in the anti-clockwise direction brings about the reduction of the speed in the downward motion of this loaded cage. Just like in all other quadrants, that is in the first, second and third quadrant, the load torque was always in the opposite direction as that of the torque which is produced by the motor. Similarly, in this case also, the load torque direction will be opposite to that of the motor developed torque. So in this case, the motor developed torque is in anti-clockwise direction. Therefore, the load torque will be in clockwise direction. From the conventions of this fourth quadrant also, you can say that the operation is of reverse braking mode, because if you see in this fourth quadrant, the torque direction is positive and the speed direction is negative. Therefore, the power developed will be of negative polarity, which clearly indicates that the energy conversion is from mechanical to electrical one, that is braking operation. Since the motion of the cage is in the downward direction, it is indicating the reverse direction. So the fourth quadrant operation clearly indicates the reverse braking mode of operation. Hopefully all this four quadrant operation explanation is very clear for you. The theory portion of the same discussed here are mentioned in the upcoming slides. It's not necessary that a hoist system must be always taken as example for explaining this four quadrant operation or multi-quadrant operation. You can also consider the case of an electric vehicle which is moving in the uphill direction and downhill direction for explaining this four quadrant operation. Consider it as a homework and try it by yourself. That is the example of a electric vehicle moving in the uphill direction and in the downhill direction used for explanation for this four quadrant operation. In all these four quadrants, the red lines are indicating the load torque. If you see in the first and fourth quadrant, this red line is representing the load torque due to this loaded cage. Whereas in the second and third quadrant, this red line is indicating the load torque due to the empty cage. If you see here, the load torques are represented as constant ones. That is, there will not be occurring any variation for this load torque with respect to the speed. This is because the hoist mechanism which we have taken into consideration for understanding of this multi-quadrant operation will be actually a low speed hoist one. So in the case of low speed hoist one, the effect of friction and windage can be neglected. So the major component of load torque will be due to the effect of gravity. This seems to be a constant one. It does not have any dependency with speed. So in this first quadrant and fourth quadrant, the effect of gravity which is being caused by the loaded cage is actually the load torque, and it is indicated as a straight line which is represented as this red line, as you can see it very clearly here. In further analysis, I can say that in the first quadrant operation, the motor torque is actually in the counterclockwise direction, whereas load torque is in the clockwise direction. The motor torque which is in the counterclockwise direction is assumed to be the positive torque. So all of you might have a doubt, since this load torque is of opposite polarity, definitely it must be of negative value, but here it is indicated as a positive load torque one. How is that possible? As the motor torque in the counterclockwise direction is indicating the positive torque, the load torque which is opposite to the direction of the positive motor torque is indicating the positive load torque. Please listen very carefully. As the motor torque which is in counterclockwise direction is indicating the positive motor torque, the load torque which is opposite to that of the positive motor torque is the positive load torque. That's why even though the direction of load torque is in the clockwise direction which is opposite to that of the motor torque, here it is having a positive sign. Hope it's clear for you now. Just like in the first and fourth quadrant, the load torque is positive in sign, and this load torque is due to the loaded cage. In second and third quadrant, the load torque which is due to So far we have discussed the 4-quadrant operation of electric drives. Usually this 4-quadrant operation are asked as essay questions in the university papers. It's not necessary that you must explain it while taking the example of hoist system. You can also explain it while considering the example of a electric vehicle having motion in the uphill as well as in the downhill. Consider this as a homework for you, that is the explanation of 4-quadrant operation or multi-quadrant operation considering the example of electric vehicle both in the uphill motion as well as in the downhill motion. All of you can explain this 4-quadrant operation with the example of this electric vehicle, and you can share your explanation in our WhatsApp group. Next we are going to study the topic steady state stability in electrical drives. From the fundamental torque equation, that is T minus TL is equal to J into d omega m by dt, it's very clear that equilibrium condition. If you see in this characteristics, the red line is indicating the motor torque characteristics, whereas this green line is representing the load torque characteristics. A is the intersection point. At this intersection point, the motor torque is same as that of the load torque. That is, at point A, the motor load system is said to be in equilibrium or in steady state. Suppose due to some disturbance, if this drive comes out of this steady state or equilibrium point, and if the drive is having the ability to bring it back to this equilibrium point, then that particular drive is said to be steady state stable, because even though due to the effect of the disturbances there was a deviation from the equilibrium point, but the drive or the motor load system is having the ability to bring it back to the steady state, then such a system is said to be a stable one. So we have to obtain the condition for the steady state stability. So for that we will consider these two examples. In this example, if you see, the motor torque is, for that we will consider the equilibrium point A. Suppose due to the disturbance there is occurring a reduction in speed which is represented by delta omega m. At this new speed, if you observe, the value of motor torque is very much greater than that of the load torque. Since the value of motor torque is greater than load torque, definitely this will result in the acceleration effect. Considering the fundamental torque equation T minus TL is equal to J into d omega m by dt, since the value of T is very much greater than that of the TL, since torque is indicated along the x-axis, the value of Tm is greater than the value of TL. So definitely the value of J into d omega m by dt is positive one, which is clearly indicating that it is creating an acceleration effect, and the operating point will get shifted to the equilibrium point A itself. That is, even though due to the disturbances there occurred a reduction in speed, but the equilibrium point is restored because the value of motor torque is greater than that of the load torque. Similarly, if due to the disturbances, means due to some disturbance, if there is occurring a increase in the speed, so when there occurs a increase in speed from the equilibrium point due to some disturbance, at that particular increased speed the value of load torque is greater than that of the motor torque. If you are assuming a increased speed point here, it's very clear that the value of load torque will be greater than that of the motor torque. So this will bring about the retardation effect and will shift the operating point to the equilibrium point itself. Now let's consider the equilibrium point B. Due to some disturbance there occurred. Now let's consider the equilibrium point B. Due to some disturbance there has occurred a reduction in speed. If you see the new speed point, that is due to the disturbance there has occurred a reduction in speed and the new speed is represented at this particular point. So at this new speed the value of load torque is greater than that of the motor torque. This will cause further retardation effect, due to which the operation point moves further away from the equilibrium point or steady state point B. Similarly, if due to some disturbance there has occurred a increase in speed, at the increased speed point the value of motor torque is greater than that of the load torque. This causes further acceleration, and the operating point, that is the new operating point or the next operating point, gets further shifted from the operating point B. Unlike operating point, while comparing the operation at equilibrium points A and B, at equilibrium point A, the motor load system is having the capability to restore it back to the equilibrium point even under the effect of disturbances, whereas at equilibrium point B, the motor load system is not having the ability to restore to this point under the effect of disturbances. So in this case, under the effect of disturbance, either the motor load system can move to a zero speed operation or its speed might go to the infinity condition. If the disturbance is causing a reduction in speed, then it will lead to the operation of zero speed condition. If the disturbance is causing an increase in speed, then it will lead to the operation into a case of infinitive speed operation. From these two characteristics, we can make a conclusive statement that for a equilibrium point to be stable one, the slope of load torque line must be greater than that of the motor torque line. It can be very clearly seen here that in this characteristics, the value of dTL by d omega m, that is actually the slope of the load line, is greater than that of the slope of the motor torque line, which is actually dt by d omega m. This conclusive statement is made from the graph. So it's very clear that for a equilibrium point to be stable one, the slope of load torque characteristic must be greater than that of the motor torque characteristics. See, if you analyze the equilibrium point B, in this case the slope of load torque characteristics is less than that of the motor torque characteristic. So in this case the point B is a unstable one. Next we will derive the conclusive remark which we have made from this graph now. That is actually the criteria for steady state stability. Suppose due to the disturbance there has occurred a reduction in speed. Initially the operating point was A. Due to this reduced speed, that is at this new speed, the operating point has been shifted. So the new point in the motor torque characteristics is this one. Initially it was at this point, and the new point in the load torque characteristics is this one. Initially it was this point. So the drift in the load torque characteristic can be indicated as delta TL, and the drift in the motor torque characteristic can be represented by delta Tm. From the fundamental torque equation we very well know that Tm minus TL is equal to J into d omega m by dt. That same relation can be written as TL minus Tm plus J into d omega m by dt is equal to 0. Now considering the effect of disturbance also, so due to the effect of disturbance, the new value of load torque will be TL plus delta TL, and the new value of motor torque will be Tm plus delta Tm, and the new speed is omega m plus delta omega. So making suitable substitutions, instead of TL we will be making the substitution TL plus delta TL, and instead of Tm we will be making the substitution Tm plus delta Tm, and instead of omega m we will be making the substitution omega m plus delta omega. Hence the new fundamental torque equation due to the effect of disturbance can be written in this form. But from the fundamental torque equation we very well know that J into d omega m by dt plus TL minus Tm is equal to 0. The same as that of the standard relation, that is Tm minus TL is equal to J into d omega m by dt. So making the substitution of this as 0 in this relation, we will be able to obtain the simplified form as J into d by dt of delta omega plus delta TL minus delta Tm is equal to 0. Expressing this small deviations in load torque and motor torque As a linear function of change in speed, we can write delta Tm as dTm by d omega into delta omega and delta TL as dTL by d omega into delta omega. Thereafter make the substitution in this relation. So this relation gets simplified into this particular form. Further dividing this whole relation by j and bringing the second term to the right hand side, we will be getting this relation in the standard form dy by dx is equal to ky. From the solution of differential equation, you very well know that the solution of dy by dx is equal to ky is y is equal to c e raised to kx. That is after dividing this whole relation with j and bringing this portion into the right hand side. The term y will be same as that of delta omega and x is equal to t. So dy by dx is equal to k into x and the value of k will be minus 1 by j into dtl by d omega minus dtm by d omega. So it is in accordance with the standard form dy by dx is equal to ky. Solution of that differential equation will be of the form y is equal to c e raised to kx. So y is equal to c e raised to k into x. In our case the value of x is k and y is delta omega. The value of c, which is actually a constant, is indicated as delta omega 0 here and the value of k is written here, which we will be obtaining from the standard form. So this is actually indicating the relation for deviation in speed. For a stable system, the value of exponent must be a negative one, then only the deviation will be minimum. Or else we can say that only when the value of the term in the exponent is negative 1, the speed increment will disappear with respect to the time, because only if it is having a negative exponential, as all of you are aware about the graphical representation of e raised to minus at, it will be exponentially decaying on. So only when the value of the exponent is a negative one, we will be getting a exponentially decaying signal. So for this to be a negative one, the value of dTL by d omega must be greater than dTm by d omega, or else we can say that for this whole term to be a negative one, the term inside this bracket must be a positive, which is possible only when the value of the first term is greater than that of the second term, that is dTL by d omega is greater than dTm by d omega, from which we can state that the steady state stability condition can be achieved only if the slope of low torque characteristics is greater than that of the motor torque characteristics. So that is the condition for steady state stability, or we can say that that is the particular criteria for steady state stability. Hopefully the solution, the mathematical solution which I explained here is clear for you. This is from the solution of a differential equation which you have studied in your mathematics classes. That is, whenever the differential equation is of the form dy by dx is equal to ky, then its solution will be y is equal to c e raised to kx. So what I have done here is I have divided this whole relation with respect to j. After doing that, I have taken this particular term to the right half of this relation. So along with this term there will be a minus 1 by j term also, because I have divided this whole relation with j. Thereafter only I have taken this second term to the right half side. So the relation will be of form d by dt of delta omega is equal to minus 1 by j bracket this term into delta omega. So minus 1 by j into this term will be k, and this will be the y, dy by dx. Y is delta omega and x is actually t. So the solution for this will be y is equal to c e raised to kx, y is equal to c e raised to k into x, and the value of k is minus 1 by j dtl by d omega minus dtm by d omega. Since this delta omega is representing the deviation in speed, as time increases the deviation must reduce to a 0 1. The deviation must reduce to a 0, not the speed term which has to be reduced to a 0 1. So for this deviation to be reduced to a 0 1, this expression must be a exponentially decaying one. For this expression to be a exponentially decaying one, the power or the exponent term must be of negative value. For this term as a whole to be a negative one, the term inside this bracket must be a positive one. That is achieved only when the first term is greater than the second term, from which we can clearly say that the steady state stability condition can be achieved only if the slope of low torque characteristics is greater than that of the motor torque characteristics. With that, we are completing today's session. All of you must try to explain the multi-quadrant operation while considering the example of an electric vehicle in the uphill and